The last topic that we discuss in this course is the topic of radioactivity and what happens when atoms are put together in a way that makes them unstable and likely to fall apart. So, for this subject, we're going to be looking at three different types of radioactivity. We're going to be looking at how much that radioactivity is able to go through things and how it's able to affect us. And finally, we'll be discussing this concept called half-life, or the ability of something that's radioactive to slowly break down into something less complicated, or at least something more stable. So, before we can really start talking about radioactivity, we have to kind of remember a couple of the basics of the structures that we dealt with last week. So, to kind of get us started, let's pretend that once again, we have an atom, and in the middle of the atom is the nucleus. And on the outside of the atom, we have our electrons. They hang out here. And inside of the nucleus, we have protons, and we have neutrons. So this is our basic model for the atom. And like I said, it's not 100% accurate. It's just a really good way of kind of picturing something that is far too small for us to picture. Now, radioactivity is what happens when something like this begins to break down because it's unstable. And in order for us to figure out what makes something unstable, we have to really look at what's going on inside of the nucleus. So let's zoom into the nucleus just a little bit. And if I have a nucleus, I might have a whole bunch of protons. In this case, I'm going to go with 5 protons here. And they're all inside of the nucleus. And I might have 3 neutrons present. Now, in an atom, neutrons act as the thing that holds the atom together. So if I don't have enough neutrons, the nucleus of my atom is going to begin falling apart. It's unstable. For small elements, we want to try to have the same number of neutrons as we have protons. So if I have 5 protons, I want to have 5 neutrons. This would be a stable atom. But if we start losing neutrons, all of a sudden the glue that holds the nucleus together starts getting weakened. And what we see is that this atom is going to go through the process of radioactivity. And radioactivity is when something comes out of the nucleus and the atom starts throwing pieces of itself off, kind of like a toddler having a tantrum and picking something up and throwing it. It's unstable, and so it starts throwing things in an attempt to stabilize itself. And that's kind of the best way of looking at radioactivity. Now, one thing to note about radioactivity is that this is not something that is rare. Radioactivity is functionally everywhere. The Earth itself has a small amount of radioactivity. There are radioactive elements in the Earth. A lot of them are further into the core, and they kind of radiate as they break down. The sun is emitting a certain level of radiation. Radiation is everywhere. So when we're talking about radioactivity, I don't want you to just think about nuclear power plants and like the disaster at Chernobyl, or if you're familiar with like the city of Pripyat. Those are not the only radioactive events. In fact, you are currently radioactive. There's a small amount of radiation that lives inside of all people just because of the elements that we're made up of. And so radioactivity is really everywhere. And what we want to avoid is increasing our amount of radioactivity. Because there is a certain point at which humans just simply can't take any more radioactivity. And just like an atom starts falling apart when it becomes unstable, humans begin to break down if there's too much radioactivity inside of our system. Our cells start to erode. They start to kind of burst on their own, and people start experiencing things like internal bleeding and stuff like that when there's too much radioactivity. But we all have at least a little bit of it. So don't start thinking that this is something rare. This is definitely something that we have kind of all over the place, and you should be used to the idea that things are radioactive. Now, when we're discussing radioactivity, we need to take into account that there are 3 major types of radioactivity that you're going to be dealing with. Some things will emit more than one type, but you should kind of be familiar with our 3 different types of radioactivity, and you're going to be doing an assignment based on those 3 different types of radioactivity this week. So, our first type of radioactivity is what's called alpha. And so alpha, which is also symbolized by this symbol right here, which is a Greek letter, an alpha radioactive particle is when the nucleus starts to break down, and what happens is that it throws off 2 protons and 2 neutrons at the same time. So we're getting rid of, I should probably spell that correctly. There we go. We're getting rid of 2 protons and 2 neutrons, so we're getting rid of 4 total particles, and that is alpha radiation. That is something that it's going to try to do when it stabilizes itself. So to kind of give this as an image, let's go ahead and create an atom. And I'm going to go ahead and use Legos again as an example. So here I have an atom. I'm going to use those as protons. So I've got 5 protons. 1, 2, 3, 4. I'm going to have 4 neutrons, and they cluster together inside of the central nucleus. And if I've got 5 protons and I want this thing to be an atom and not an ion, I need to have 5 electrons basically spinning around the outside. So we've got some yellow electrons, some red protons, and some gray neutrons. So when we undergo alpha radiation, what happens is that our nucleus becomes unstable, and in order to stabilize itself, it is going to cast off 2 protons, so 2 of my red Legos, and it's going to cast off 2 neutrons, 2 of my gray Legos, and they are going to leave. Now what happens is that my remaining particles right here are now lower energy state and they are stable, but after these particles over here have left, we now have a different atom. Where before I had 5 protons, and we said protons determine what type of element we're dealing with, I now have only 3 left over. Which means if I go and I take a look at my periodic table, which I introduced the idea of last week, before when I had 5 protons together, I had an element called boron. It's right here, number 5. Now that those 2 protons have left, whoops, go back. Now that those 2 protons have left, I only have 3 left over, so now I have something called lithium right over here. So my element has changed its identity because I have changed the number of protons involved. And so one thing that you'll find out during alpha radiation is that atoms start becoming other types of atoms when it happens. Now you'll also notice I have 1, 2, 3, 4, 5 electrons that are still on my atom. I have only 3 protons, so if I have 1, 2, 3, 4, 5 negative things and only 3 positive things, this thing now has a -2 charge. So it is negatively charged because I have more negative things than I have positive things. So our second major type of radiation is radiation called beta decay. And we're going to be looking at specifically beta negative decay, but for the sake of this course, we're just going to refer to it as beta. So I'm going to go ahead and kind of put my atoms away here. And so we're going to be looking at beta decay, which is represented by the Greek letter that looks just like a big B. In beta decay, what happens is that what used to be a neutron, and remember, neutrons have no charge, neutrons are really just a combination of a positive proton and a negative electron. So if I stick these 2 things together, this one being positive and this one being negative, they become a neutron. And in beta decay, that process gets undone. And what happens is that I lose my neutron, it becomes a proton and an electron, and then the electron says, I'm out of here, and it leaves. And we're left behind with just an extra proton in our beta decay. So let's go ahead and kind of do this again as a model. So once again, I'll go ahead and start with 1, 2, 3, 4, 5 protons grouped up inside of my nucleus. This time I'm going to go with 1, 2, 3, and 4 neutrons in my nucleus. And if I've got 5 protons and I want this to be a correct atom, I'll go ahead and have 5 electrons. So once again, I've got my nucleus here, electrons on the outside, and everything that's going to happen involving our beta decay happens inside of our nucleus. So in beta decay, one of my neutrons miraculously splits apart, and so I'm going to leave that, and I gain, oops, wrong color. I gain a proton, and I gain an electron. The proton is going to stay here. The electron leaves the whole system. It doesn't even stay with the other electrons. It leaves altogether. And so now I have 1, 2, 3, 4, 5, 6 protons, where before I had 5. So again, this is going to be another change in element. So in beta decay, I'm going to increase my number of protons, which means at one point I had boron, I now have carbon, which is 6 protons. And 1, 2, 3, 4, 5, 6 positive things. 1, 2, 3, 4, 5 negative things means this thing has a positive 1 charge. So this atom right here is a carbon atom with a positive 1 charge, and if I was to demonstrate nuclide notation like I did last week, I could see that I have 6 protons, and I have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 things in my nucleus. So again, in beta decay, we wind up changing the element that we're dealing with, and you're going to find that's kind of a pattern, especially with those first two, well actually with only those first two types of radioactive decay. What we have is that we've got elements turning into other elements. Now our last one is the most dangerous, but it's also the most easy to explain. So the last type of radiation that you might see is gamma radiation. Gamma radiation is represented by kind of a squiggly looking Y, and no, if you take an overdose of gamma radiation, you do not become the Hulk, you become dead. See, gamma radiation is the highest energy radiation that's available. It's extremely high energy, it's easily the most dangerous by far, and it's the most difficult to deal with. And we are lucky that we have a magnetic force field around the Earth, otherwise there would be a lot more gamma radiation hitting us and we'd have a lot fewer humans. So, in gamma radiation, what happens is that I have an element, so let's use the same element as I had in my last example, carbon 6 plus 1, and all it does is it turns into carbon 6 plus 1. Nothing changed. The only thing that really changes is that I get a packet of energy that leaves the atom. And so this one right here is kind of like a low energy version of the same thing that we just had. And this little ball of energy just kind of shoots off and does its own thing. So modeling that is really easy. I don't have to model it for you because really nothing changes. Now, the thing that you do want to know is that that tiny little ball of energy is something that we refer to as a photon. A photon is a packet of energy that is able to move through space on its own, kind of together. So there's no mass on this thing, it's just a pure ball of energy as it moves through. And because it doesn't have any mass, that means that it's able to go through a lot of things, and it's able to cause a lot of problems, especially if it gets inside of you. Now, if we want to protect ourselves from radiation, it depends on what type of radiation we're dealing with. So if we're dealing with alpha radiation, you can actually stop alpha radiation with a piece of paper. Remember, alpha radiation is 2 protons and 2 neutrons. This is a fairly large particle, relatively, so it's not able to fly very fast or go very far. In fact, a few centimeters of air is enough to stop alpha radiation, but realistically you could block it with a piece of paper. Your clothing is good at stopping alpha radiation. It is by far the least dangerous one that you have to deal with. But if we're going to step this up and talk about some like beta radiation requires about 1 centimeter of aluminum. So you want to put 1 centimeter of pure metal between you, or about 1 meter or 3 feet of air. So as long as you are 3 feet away from something that's emitting beta decay, you will be okay. That was bad. That was a bad pun. But let's be real. If you're social distancing from beta decay, you're not going to get injured. So that one's fairly simple. Not super dangerous unless you are extremely close up to it. But the one that you really have to worry about is gamma. Gamma radiation is the kind that causes a whole lot of problems because you need somewhere between 2 to 4 centimeters of lead or a full meter or 3 feet of concrete if you are going to try to stop gamma radiation. Gamma radiation is the kind that we are truly afraid of, and it's the reason why when you go into the dentist's office or the doctor's office and they want to do an x-ray, they put that big heavy lead vest on you. Is that what they're doing is, even though x-rays are mostly non-harmful, if there's a small amount of gamma radiation being produced, the lead vest will actually catch that and stop it from entering your body. And that is what they are mostly concerned about, is trying to stop that from getting inside of you. And that's why we take such precautions when it comes to doing x-rays. What reasons why your x-ray technician can never be in the same room as you is that they might do multiple x-rays per day, and that radiation builds up inside of them and can make them really, really sick. So that's a couple of ways that you could protect yourself from our 3 different types of radiation. Last up for this unit is an essential concept when you're trying to figure out how long something is going to be dangerous for, or how long something is going to be radioactive for. We have to talk about something called half-life. And half-life is represented by the Greek letter lambda. And this is the way that we calculate how long something is going to be radioactive. And literally, half-life is the amount of time it takes for half of something to go away. In this case, we're talking about half of something radioactive, and it's not just leaving, it's decaying. So how long it takes for something to undergo radioactive decay for only half of it to be left. So if we're dealing with something like half-life, it's really easy to show this on a graph to kind of give you the idea. Because what happens, and this is what most people don't expect, let's say I have 50 kilograms of radioactive material. After one half-life, so this is one half-life, I now have 25 kilograms of radioactive material. That makes sense to a lot of people. What happens next is the part where I catch people sleeping. After the second half-life, I don't have 0. This is wrong. After the second half-life, I have 12.5 kilograms. I did half of this number right here. And if I was to keep going with this, so half-life, the third half-life is going to be 6.25. I can confirm that. 6.25 kilograms. And as we keep going, so this is going to be 3.125 for the fourth half-life. And it just progressively gets smaller and smaller and smaller through the fifth half-life, the sixth half-life, the seventh half-life, and what you will realize really, really quickly, this is going to be 1.5 something, roughly 1.55, we got 0.75, I don't know. At this point, the numbers are getting really tiny. If you are any good at math, you will quickly realize that you can divide something in half as many times as you want to. You will never, ever, ever get it to 0. And this is the problem with radiation, is that something that is radioactive will always, always, always be slightly radioactive all the way until it breaks itself down to one single atom left of that substance. And considering that everything is made up of bajillions of atoms, this is going to take a very long time. So previously I mentioned a radioactive disaster at a place called Chernobyl. That place is still radioactive today, even though the disaster happened a long time ago, and it will continue to be radioactive for a long time. Same thing with places like where they've tested or dropped atomic bombs. Those places are radioactive and continue to be radioactive for a while because half-lives is the way that things break down, and they never totally go to zero. So kind of, if I was to plot this on a graph, where this is my mass of radioactive material and my time is down here, I'll use a different one. What happens is that it decreases very quickly and then eventually starts to drag out as we get closer and closer and closer to zero, but we never get to zero. And so this is the easiest way to identify something that's undergoing a half-life, is that it's going to decrease really quickly at first. It will never quite hit zero, and every time we go through one half-life or one time interval, it's divided by 2, but it's always the previous number. We're never going to wind up getting to zero. So that is radioactivity in a nutshell. It's not a terribly complicated thing, but it is something that you should definitely know, and it is also the last thing that I have to teach you for Introduction to Physics. So if you are one of the people still watching this video and you've been staying with me the entire year, congratulations, you've now covered everything that is in my course.